So let's look at what is the cascade. So the reason I said this, just want to know that we are not jumping to another topic. We're still talking about this paper to help us understand this paper, right? But we have not learned the cascade amplifier. So let's go back to what we have learned earlier first. This is a common source amplifier we learned at the beginning. And we say we use the inductive loading, right? What is the advantage of inductive loading? Very good. So this has a large headroom, right? Because your drain can go to VDD, and that is what you're doing in your project, right? You actually the drain is very close to VDD. If it is not, your M2 is going to be in linear mode more easily now, right? The cascade one, and also no noise, right? Compared to resistor, because now I have a large gain, but I have much smaller noise, only RS. The problem is that at that time, then how do we match the impedance, right? We actually rely on the feedback capacitor, which is CGD, coupled with L1, all this network together to do the impedance matching, which works pretty well. But you have a chance to get into oscillation because that impedance can have negative value for certain frequency, right? We spend a few slides to go over that, right? I don't expect that you can derive it in the exam, but I hope you can follow if someone tell you about this. That was the problem, right? So if the impedance in the input change, you mean here, you will, because it's coupled to the output, and more difficult to design, right? Yeah, because it's like feed forward directly. Yeah. Okay. A good point. So you hear what he said, right? My teacher. So when you're doing your cascade, remember you kind of decouple it. You do your input design, and then the output design separate. Output impedance and input impedance, right? You no need to worry that now I match the input impedance and later I try to change the loading to reduce the gain of my LNA, then it's going to affect my input impedance. That can kind of decouple. This one just fully heavily coupled, right? So if you try to adjust the input impedance, or later you decided, oh, I'm wrong L1 because I actually now I realize that let's say my L1 parasitic capacitor is too large. I want to further increase the L1. And once you increase it, then you need to redesign the C in, right? So it's just like what he said iteratively, right? So what can we do? Then the idea is that let's do not get the matching by using CGD and L1. Let's use inductive generation. You have not learned it, we will show it. But you learned the inductive generation in common gates already, kind of similar. I mean, the idea is kind of similar. You have a generative degeneration inductor, right? That's the first thing. Second thing is that if you want to avoid the effects of L1, like what he said, right? We add a cascade to it. Then you can decouple the input and output, okay? Here you still don't know what I'm talking about. The main point is you review what happened before, right? This is okay? Then let's start playing with the math. A lot of math, but it's interesting. So this is the goal. We're going to add a degeneration inductor at the source. And naturally, I have CGS1 because gate source has a capacitor, right? And then now my question is, what is the input impedance? Fine. C in. But we are trying to make it simple. Ignore CGD and CSB. Okay? We know we have many capacitors, right? You have CGD, you have CSB, they are connected together. We have four capacitor usually, right? And CDB, right? CDB is out of picture because it's here. So good. So we said we will ignore this. Then let's start just KCL, KVL. First, this is VP, right? You see P. What is the value of VP? This is Ohm's law. So it is equal to Ix, the current. This current is going to flow through here, right? Correct? And Ix is here from the source. Yeah, it's just AC has microwave, right? It will go through the CG as well. Yeah, so that's a good point. He said, make sure it's AC because this is a capacitor. But of course, we're talking about AC is microwave high frequency, right? So it is the current go through here. And you have another current, which is the current go through here, right? So I think I don't want to follow my cheat sheet, but I want to ask you one thing first. What is VGS? VGS equal to what? VGS equal to Ix times 1 over SCGS1. Do you understand what I mean? Ix times 1 over SCGS, right? Because this is just Ohm's law. Because this is the impedance of the capacitor. Current times capacitor give me the voltage, right? Good. I want to highlight one thing. This is Ix. At the same time, I also have current Im. Let me call it Im. Again, of course, these are all small signal. What is the relationship between Im and CGS? GM times VGS. I don't want to say CGS. This one I say many times is very important. Is this okay? Transistor, this is most fundamental thing. The change of the drain current is equal to the GM times the change of the gate voltage. You need to memorize this, even you don't understand now, right? Okay, good. So what is VP in this case? Again, Ohm's law is Im plus Ix times SL1. Ohm's law. The total current comes in, go through the resistance, the impedance of the inductor. And then I plug in what I just had. I keep Ix. And then Im is just equal to GM times VGS. But VGS is just what? Ix divided by SCGS1, SL1. SL1 I just copy. Ix I just copy. Im is GM times VGS. VGS is Ix divided by SCGS1. Is that clear? Now I tell you, in the textbook, they just give this one directly because they assume that you're very familiar. You already can see it, right? But we just do more steps. That's the first thing. And because of this, not yet actually. And then now, how about Vx? Again, we use KCL. Vx equal to VGS plus Vp, right? KVL. Vx equals to Vp plus VGS, right? Total voltage here, this voltage plus this voltage. Oh, I'm blocking you. Right? Is that okay? So I'm going to just plug in. Then in this case, I have Vx. I want to keep Vx because I'm looking for Cin. Cin is equal to Vx divided by Ix. Right? So Vx equal to, I don't want CGS. I don't want VGS. And VGS is already given here. This one, right? So VGS is equal to Ix divided by SCGS1 plus Vp. And Vp is very long. I just copy everything. Ix plus GM Ix divided by SCGS1 times SL1, right? By using this, now I have Vx equals to VGS, just this term, plus Vp, just this whole term. And now I have everything in Vx and Ix. So now I can find the input impedance. So I would say just Zin equal to Vx divided by Ix. And it is pretty simple because you see this is Ix times a constant. This is Ix times SL1. This is Ix times a constant. So I just need to put Ix here, and then the rest is the input impedance is equal to 1 over SCGS1 plus SL1 plus GM SL1 divided by SCGS1. But this S can get cancelled. Right? Let me check my cheat sheet. There's a lot of math, but can you tell me which one is the real part? Exactly. This is the real part of Cin. Right? So you just set GM L1 CGS1 equal to 50 ohm. That's what we mean by we try to match the input impedance by the degeneration inductor. Now we are not relying on this loading inductor. Of course, we have not drawn it yet. You don't know what is upstairs. We're going to use a Cascode transistor. But here just show you that we successfully done this, right? But there's one problem with this that we need to be careful. So what you see is this. In 65 nanometer, right? I forgot to say one thing though. What is GM divided by CGS approximately equal to? Very good. Omega T times L1. So basically now, your input impedance equals to the transit frequency times the inductor, right? Now that is the problem. When you go to newer technology, the transit frequency is going to increase. In 65 nanometer, right, it said that the transit frequency is about 2 pi times 160 gigahertz. And you just plug in order to get 50 ohm, I will need an inductor that is 50 picohenry. Yeah, that is very small, right? So the first thing, because it's small, we will just use the bond wire. So what does it mean? This is your chip. This is the source. This is the drain. This is M1, right? You recognize the layout, right? This is the gate, right? Do you see this? You reckon? So actually, not I'm wrong. The drain, because this is using, what do you call? A finger structure. Only the middle is the drain. The outside is also the source, right? But the point is that the source, we don't create any inductor. We just put it to a bond wire, and this is the ground. This very tiny bond wire, we hope that it is very small. But no, usually it's too large. It's even smaller than the bond wire. So this is one issue that need to solve, right? I don't know how people solve it, but we're looking in another issue is that because of the bond pack capacitance, you are going to reduce you are going to increase the inductor you need in order to match it. So you're going to reduce your impedance that you will see. Instead of 50 ohm, you may become reduce it actually. Instead of 50 ohm, become 12.5 ohm. So you can increase your inductor by 4 times, which will be better, right? But that's okay, not for our class. up to this level, the main point is I hope that you gain better skill in solving circuit in this way, right? It's really a jump for you for those did not take E124, but I mean, even by inspection. Second thing is to recognize this. We use inductive degeneration, and now we rely on the inductor to match the input impedance. Then we need to change our mind because we always think that, hey, inductor is imaginary. How can you use it to match 50 ohm? It's just the whole circuit, you put it together, you come up with you will have a real part. And that real part depends on your inductance, right? Which is omega t times L1. Right, so this type of idea is like eye-opening for us who have not thought about this, still have the idea of just inductor, capacitor, and resistor. But when you combine them with an active circuit, you can use it to change the real part, just because you mess up all the different terms, right? And this is a very nice way. So we will continue to understand why the bond pad is an issue. Before that, I want to review another concept in the transformation, in circuit transformation, right? So let's say, again, I won't test you this, but it would be good if you understand this and then you know where to check in the future. So I have a resistor, which is Rs. And then I have a reactive impedance, JX1, right? So this can be capacitor or can be inductor, okay? So I look into here, I see a input impedance. I call it Z in S because it's seriously connected. So I want to show, I'm not showing that, but I just give you the equation. This is equivalent to another circuit that you make it parallel. You still have JX1 here, that you put it in parallel. Okay, so you have, let's say, 50 picofarad capacitor here. Now you put 50 picofarad in parallel. What should I do to this resistor so that they has the same impedance? And I call this RP. So the goal is that if I look in, this is Z in P, right? The goal is to have Z in S equal to Z in P. That's the question. Now, then you can go to textbook in chapter 2, take a look, or you just trust me. In order to do that, a very quick way to find it, right? Of course, you can solve, right? You just solve the circuit, find out what is the input impedance, and then equate that. Then you know under what condition they will be the same. But one quick way is that we know that for high Q, when the Q is very high, for large Q, think about this. If Q is infinity, S must be 0, right? RP must be infinity, right? Then they are just equivalent circuit, right? So you will just hand-waving way of memorizing it. So if it is in very large Q, then I will expect C in must be C in P, right? That automatically satisfies. But if they are the same, then I also expect QS equal to QP, the quality factor, right? So that is something help me to memorize. So what is QS? On the left, we just discussed earlier. No, we were talking about parallel, but how can you make it a high Q? You prefer small s or RS or large RS for high Q? Small, right? So it must be at the bottom, right? Then the top is going to be JX1. Yeah, J is the imaginary number. Square root -1. And then it needs to be QP, and what is QP? We just discussed for parallel. RP divided by JX1, right? But however, always just don't mess up. We need the magnitude. We're talking about Q, okay? So with this, what does it mean? It means X1 squared equals to RS times RP. So it also means that RP must be equals to X1 squared divided by RS, or RS equal to X1 squared divided by RP. Right? We did not really prove it, but the point is that if you have a impedance, if you have a circuit like this, you can transform it to be the same for the frequency that you're interested in. This is approximation. If you change RP to this one. Okay, so memorize this equation. X1 divided by RS, X1 squared divided by RP. Okay, so this is just a first step to help us to memorize something. Now, then the reason I do that is we want to ask. We just now talk about this circuit. I have CGS1, I have L1, and I match it very well, right? I get 50 ohm. But unfortunately, right, so I have CGS1, I have R1, but unfortunately, by the way, what is R1? R1 is the 50 ohm we just matched. Okay. I kind of skipped oh no, sorry, I say it wrong. L1 is L1 is the L1 is the degeneration what's wrong with me?
Yeah, R1 is your resistance after you put source degeneration, and L1 is additional inductor to match the flip field.
No. L1 is this one. Yeah. Anyway, let's finish this circuit first. Yeah. So okay, so let's start with this circuit, right? Originally, I don't have this. Oh, okay, so I know. R1 is 50 ohm because no.
Yeah, this is your source, right? So
I'm kind of confused why they have. Okay, let me take a look. Yeah, LG is the one to cancel the stuff. Let me see. Yeah, R1 is the. Okay, I know. R1 is the real part. Eventually, I get it right. R1 is the real part, which is the 50 ohm. Okay, so this is a little bit, I keep forgetting about this. Can we look at this? Do you remember what's the input impedance? 1 over SCGS1 plus SL1 plus 50 ohm. Do you see that? That was the input impedance. How do you model this one? Capacitor in series of inductor in series of resistor. Right, so let me draw this circuit. So that's why I got confused, right? So here, this is also called R1 later, right? So this is like this. This circuit is like this. You have L1, CGS1, and then R1. What do you mean by source? Vx. No, I'm talking about looking into this direction, right? Looking into here, I get Z in. Next slide. Yeah. No, I look into here. The effective impedance is equal to this imaginary part plus this real part. It doesn't need to be a physical one, but it turned out it's this imaginary part plus this real part, right? After we solve the circuit. Do you agree? Yeah. And isn't this is equivalent to have L1 in series with CGS1 in series with R1? If I try to find the input impedance of this circuit, it's equal to Z in, right?
Yeah, but this all works if your source is. That's how you get maximum.
Source.
Source you funded the.
No. It doesn't matter about the source. It depends on how I want to match. This R1 doesn't need to be 50 ohm. It's just an equation.
Yeah, so that's right.
So if I look into here, that's all I see. Nothing to do with source. And if I want to match the source, yes, I will make R1 equal to 50.
Yeah, so in this case, you're right.
No. When I look into here, isn't this is exactly the same circuit? Now, then we add the bond pad. Before that, we don't have bond pad. No. The source come from the pad, right? So that's a good discussion. So, we can look at this one. Oh, no, we don't have the pad. So you are this, right? You have this transistor. This is common source, right? You actually, this source go to the pad, not source. The gate go to the pad. And then you come in, maybe the antenna. This is the 50 ohm antenna resistor. This is V in. So what we are looking at now is here. That's why I have a pad. And then plus whatever model we had earlier. Does it make sense? I just told you, well, look into here is equal to inductor plus capacitor plus R1, right? Just at this point, at the gate.
Okay, so that's no gate.
Yeah, this is the gate. Yes. Yeah. So do you get? I mean, he has a good question. Do you see what I'm talking about, everyone? Not into the source. We're looking into the LNA. Exactly. So I confuse you guys. Actually, it's 46. Let me just say one more thing, right? This is important. What I'm saying is that we solve all the KCL, KVL. We found that the input impedance is this plus this plus this. Not even need to understand what it is. It's just an imaginary part plus a real part. That's it. I can model this one with L1 in series with CGS plus R1 just because of the math. Because this math turned out to be SL1 plus 1 over SCGS1 plus R1. Right? This L1 is they don't have the same configuration anymore. We don't have the transistor. This is just the model. And now, what he's saying is that, then where does the CPAD come from? The CPAD is because this is your design, and then you have pad, and you have bond wire go to the antenna. Here is the source driving you. So 50 ohm is here. So that's why I have a CPAD as the parasitic. And then I will see the same equivalent circuits afterwards. Okay, let's stop here. Thank you.